So the first topic is focusing, which I'll start with. And Pierre-Louis has specifically asked me to cover this, and I'm also happy to do it because I think it's very important. Several people have asked me also to elaborate on this idea that you can have a type-theoretic version, a logical version of quote and eval that we know from dynamic languages. And so I'm going to try, after discussing focusing, to give you an introduction to that as well. So we'll see how it goes. Hopefully time will last. Okay, so let's start about focusing. Focusing really decomposes into two pieces. Okay, and as I said last time, focusing, well, one easy access to focusing, if you want to understand what it does, is to try to remove redundancy from the search space that you create when you work with sequence. Okay, so the basic problem is that with sequence, you have many different ways of proving things, too many ways in some sense. There's too much non-determinism in the search. And so we're trying to remove that redundancy, that non-determinism from the search space. So I think there's a kind of progression here which I think we should keep in mind. And this is a universal observation. I don't know that there's any logic or anything that I've looked at that doesn't obey this, that you have a natural reduction, and then you can build a sequence calculus as a calculus of proof search for natural deduction, no matter what the logic. I gave you many examples, right? It seems it all works in these. And then to remove redundancy from the sequence calculus, you get to a focused sequence calculus, okay? And all the logics I know of, linear logic, modal logic, ordered logic, temporal logic, you name it, seem to satisfy this. So this is a universal observation, okay? Of course, it's not a theorem, it's just an observation that this is the case. So I think this is the natural next step, so it's very important if you're going to work with logics to know about that and at least know the outline of it. Okay. So the easy part of focusing, if you will, is inversion, okay? So inversion, Pierre-Louis mentioned it yesterday, he called certain rules reversible, okay? Is the idea, if you look at a proposition, okay, either on the right or left, depending on whether you know it or you're trying to prove it, you can apply the right or the left rule in the sequence calculus without ever looking back, okay? So for example, if you have something like this. So by the way, today, I'm going to write the sequence like this. I write gamma, single arrow A, and it means that A has a focus proof. Okay, it's just like a sequence except that I want focus proofs. Okay, so for example, okay, we always start with conjunction because it's easy. A focus proof of A and B decomposes into a focus proof of A and a focus proof of B. And because it's a restriction of the AND rule, okay, we'll still call it the same. We call it the, not introduction. I should have called it the right rule for AND. We'll still call it that, okay? Okay, so the idea is that whenever you're trying to prove this, don't even look at gamma. Okay, you can immediately compose in two sub-goals and solve them independently. That's always okay. And why is that okay? Okay, so this is not a formal proof, but an intuitive statement. The intuitive statement is that this rule is invertible or reversible. Whenever the conclusion is true, okay, then both premises must also be true. Does that make sense? So in particular, if you know A and B, then A should also be true, and B should also be true. And since both of them are true, you're not losing anything when you apply that rule in your proof search procedure going from bottom to top. Does that make sense? Okay? Okay. So that's the easy part. Okay? And now we can look at the various rules, and we can see whether rules are reversible in this way. Okay? And we're going to try to arrange in the sequence calculus, okay, that if you have a sequence where you have A and B, morally, this is the only thing you can do. Well, we'll see about that. Okay. So let's think about implication as well. Okay. Gamma arrow A implies B. Well, we already know what the rule is. It's implication, right? Gamma comma A arrow B. Okay. So the question is that reversible? So this is part of our search strategy, that you will, in which we always decompose invertible things. Yes? I heard yes. Okay. So let's just try to show that, okay, because it's a good exercise. So let's go into sequence calculus, maybe over here. So we know gamma, arrow, A implies B. And we want to show somehow that gamma comma A proves B, right? Actually, after I've shown this, okay, we'll come back to the homework exercise from yesterday to show that going from here to here, if this is a turnstile, is not a good elimination rule. So I'll ask for people to give me the answer that they found. But for now, we just want to show if we can prove that, we can prove that. So how do we proceed? Well, so we know this is a sequence calculus, so we know cut is admissible. Yeah. Okay, so we start with A, you mean like this? Okay. And? Okay. Taking other thoughts, how do we prove this? Anybody see how to do it? If we know this, how do we know that? Okay, the weird thing is that we're using the rules against their grain, right? In the sequence calculus, all rules work bottom up, okay? But somehow we need to go from something downwards to its component, right, which goes against the grain of the sequence calculus, okay? So the only rule that goes against that is the cut rule, which we have as an admissible theorem about our system. So we have to exploit that. So how do we get from gamma proves A implies B to gamma comma A proves B? Do you want to weaken this, or? Okay, let's worry about weakening later, because weakening is sort of a technicality. First, we need to get the central idea of the proof. Okay. Well, we don't have implication elimination because it's a sequence calculus, so we only have left and right rules. Well, implication right here doesn't help us because it works upwards, right? And we need to deduce something from it. So implication right doesn't help. So we know this, we're trying to get that. Okay, so we need cut. That's I already gave you that hint. Okay, so in order to have a cut, we need something else with A implies B on the left-hand side, right? Right, we have that. If we can cut it against something like this to get that conclusion. What could we cut it against to get this conclusion? So we have to add A here, and we have to add B here, and then we could do cut. Okay, so this should be an admissible rule. So it's a theorem about the system, so we're not actually applying an inference rule. Okay, to get that. How do we prove this? How do we prove in the sequence calculus A together with A implies B entails B? It's the implication left rule, right? Implication left, and here we have to show that from A we can prove A, and here we have to show from B we can prove B. How do these follow? These are the identity, right? Okay, and now we need to do some bookkeeping to make sure that the weakening is applied. So what do we need to weaken? We need, in order for these two premises to match up, I guess we should have a gamma here, right? We should add A over there, but we can always do that. We just add A everywhere in the proof. It doesn't change the proof, right? So we add A here. What does this become? This becomes gamma. We keep the implication, even though we don't need it. We add it there. And what do we get here? Well, we get gamma, and we keep the implication, even though we don't need it, and we get B. Okay. So that's our proof. Okay. You see how powerful the principle of cut is. Okay. It's very simple to prove that from A implies B, you can get to gamma comma A arrow B, and you don't need any induction or anything like that. You just give the little proof of it. Okay. So for all the inversion principles that we're writing down over there, it's always the same thing. Okay. We always use cut directly in order to show that the rules are invertible. Okay. Okay. So now the other question was, why is this not a good elimination rule, which was really a very good question. Okay, did anybody find out what was going wrong when we did this? Yeah, it's hard to do an induction, yeah, but there's something in particular that actually fails. Yeah? Okay,
because if you want to get some good
yeah.
and then you have to have a good environment.
Yeah, but we have other rules that make the environment smaller. Get rid of it again.
Yeah, but then you would get the same type.
In this particular example, yeah. So, I mean, this is like the right intuition, perhaps, but it's not quite really the thing that really destroys this rule as a possibility. Anybody see what that is? Yeah? Contraction. Why?
Because we want to have it.
We want contraction to be invisible, but contraction should still be okay. Maybe not. I don't know. Okay. I had another thought about this, which is that substitution principle. Okay. So let's think about substitution. You always need to have that from gamma in A and gamma comma A proves B, you can conclude by substitution that there's a proof of B, right? You need that. Okay, because we use that as part of our reduction, right? This is a term m, this is a term n, and we substitute m for x and n in order to get the proof of the conclusion, right? It's the basic computational principle. Now, if you substitute here gamma comma A, gamma turnstile A, okay? Right, how do you continue now to get a proof of B? Well, you can't substitute into the premise because the assumption A is gone. So when you try to substitute, you're stuck at this point. Okay. So what fails is substitution. Okay. So we need to always check, in some sense, right, that the substitution principle which we need in order to explain the meaning of hypothetical judgment is still being respected. And if you had such a rule, it wouldn't be. Okay. Because we can't substitute for this assumption because, well, it's not here. There's no other way to get a proof of B. You see that? Okay. Think about it offline because I have a lot to cover today, but it's a failure of substitution which is a problem here. Okay. If you annotate it with proof terms, you might also see that because the annotation of this with proof terms would be, we have a proof M of A implies B. Okay, so here we would make a new assumption x colon A. Now we need a proof of B. What is the proof of B? We would have to make up some notation, right? Like M applied to X, something like that, right? Okay, Mx is a proof of B, okay? But now if you substitute for X, the term would be M applied to N. And what is that the proof term for? For our usual implication elimination rule, right? The one that we started with, right? Okay. So when we substitute into this, we have to substitute for n, then the proof term will be mn of type B. But in order to be able to show that this is a well-typed term, you must type it with the ordinary implication elimination rule. M has to be of type A implies B, and n has to be of type A, and then the application has to be of type B. That's a rule that we wanted to get around having by using this rule. Okay. So this rule, even though it's admissible in the sense whenever this is true, that is true, we just prove that here, okay? For the secant calculus, it's also true in natural reduction. it's not good as an elimination rule because substitution fails. Yeah?
This is a consequence of the failure of the subformula property?
Subformula property actually does hold because if we ignore this, this is an elimination rule, so you have to ask in the downward direction, okay? Because we're allowed to use A implies B, and so we're allowed to use A here, okay? But actually, you might have gotten a clue here because if you look at the left-hand side, this would be the assumption that we can use A in the remainder of the proof, okay? But in the introduction rule, we could also use A, so there is a clash. We don't flip that error around, okay? But the subformula property does hold for this rule, okay? We just can't apply substitution to that proof. Okay, so let me move forward here. So the other right rule we have would be this. Okay, it's invertible, okay, which means in this case we think about it, if we see true on the right, top on the right, we can apply this rule. We never have to look back because our proof is finished, okay. What about, I don't know, let's see, what are the other invertible things? What are the other invertible rules? Okay. Suggestions? Well, we have a number of rules left. Is there anything else that's invertible? Okay, or on the right. Is or on the right invertible? Now, there's only one situation when we know that we can invert the rule, which is that. There was a consequence of cut elimination. It's invertible if you have no assumptions, right? Because then you can prove A or B only if you can prove either A or you can prove B if you have no assumptions. But if you have assumptions, you cannot necessarily prove A or B. And the example would be something like if you have B or A, and you're trying to prove A or B. Okay? So obviously, we cannot immediately proceed on the right-hand side and either prove A by itself or B by itself. We have to wait and distinguish the cases first, right? So the right rules for or are not invertible. Okay, we can't always proceed by looking at that connective and not looking at the rest. Okay. Now, fortunately, the left rule for disjunction is invertible. Okay, we can always distinguish cases. So if we have gamma comma A or B, and we try to prove C, okay, so what we're going to do is we're going to distinguish the two cases. And here we make the first change to the system we had before. What is this change? Anybody remember the sequence calculus from yesterday? Right. So we're dropping the A or B with the idea that A or B is redundant here because we have something stronger, namely A over here, so we don't need that again. The only thing we could do is apply the left rule that only give us A again, so we don't need it anymore. And here, we drop A or B as well for the same reason, because we get B, which is stronger. Okay? Okay, and so this is because we think of these things as being properties of the connectives, that we can always do this right away. Okay, bottom also. If we see falsehood on the left-hand side, we can immediately apply the left rule, never need to look back because our proof is finished. Okay, so now the interesting fact about these rules is that when we're working in a bottom-up way, we can apply these in any order that we like. Okay, if you have a given goal that we're trying to prove, we always end up with the exact same sequence that we have to prove. Okay, if we apply all these rules. So we decompose a problem maybe into multiple problems. Okay, but the problems that we end up with are always the same, no matter which order we apply these rules in. Okay. Okay, now there is some terminology here. Okay. So we have the negative connectives. And negative means that the right rule is invertible. Right rule is invertible. And so the negative connectives here are A implies B, A and B, and true. And the positive connectives, they are the ones for which the left rule is invertible, and that's going to be A or B, and falsehood. Okay. So I didn't talk about atoms, okay, atomic formulas, because when we're at an atomic formula on the left, we can't necessarily succeed because we can only finish the proof. It happens to be also on the left. Okay. If we see an atom on the left and we look at it, we can't immediately succeed unless the same atom happens to be on the right. Okay. So looking at an atomic formula, we cannot say, okay, we can always apply the corresponding rule, which is the identity rule. We might have to wait. Okay. So they're not going to be, the atoms are not going to be invertible, but they're going to play a special role. Okay. So now, so that's the first part. Okay. So the first part of focusing is that if you see a connective that is invertible, which means that it's negative on the right or positive on the left, just break down the proposition and apply the rule and never look back. Okay. So that eliminates a whole lot of non-determinism because you can do this in a don't care non-deterministic way, and you always end up with the same sub-goals. Okay. So what does the sequence now look like after, we call that the inversion phase? Okay, what does the sequence look like after the inversion phase? No, because it could also be positive. Okay? So the right-hand side is something positive. Okay? And what do we have on the left-hand side? Okay, it could be something negative. So A1 negative, AN negative. Okay. Now it's possible that we have an atom here, or it's possible that we have an atom here. Because it's possible, we actually have two forms of atoms. We have negative atoms, and we have positive atoms, which you throw into the equation. Okay. Interesting thing is when you have an atom, and I'll come back to that later, you can actually decide yourself whether you want to consider it as being negative or positive. Okay. All right. So if you ignore atoms, this is what essentially what our sequence now looks like. A bunch of negatives on the left and a positive on the right. Okay. So it could be like an implication on the left, a conjunction on the left, or it could be a disjunction or falsehood on the right. Okay. So the question is, let's look at some examples on this, and let's see if we can now cut down more on the non-determinism. Okay, so the example I want to use, these are all simple examples, but okay, so let's say we have, okay, let me write it like this. So we have A implies B implies C. And we want to show that, let's see, if we have A implies B, then A implies C. Okay, that's an example of something we want to prove in the sequence calculus without any assumption. Okay? So so the main connective here, if you remember that this is right associative is like this, right? This is the main connective, so we apply the implication right rule, then we apply it again, then we apply it again. And then we're in a situation where it looks like this. We have B implies C, we have A implies B, and we have A, and we're trying to prove C. Okay? So now we're in a situation, like I said before, where we have things that are negative on the left and an atom on the right. And so now we have to stop our inversion phase because there is no rule that we can now apply without having to look back. Okay? Okay, so how many proofs are there of this in the sequence calculus? What are some of the things we could do now? So let's look at it. Could we apply the left rule to this? What would be the two sub-goals? One would be to prove A, and the other one would be from the remaining assumptions in B, prove C. Make some progress, right? It's possible. We might be able to do that. Okay. Could we apply the left rule for implication to this? Okay, so while the one sub-goal would be to prove A, and the other sub-goal would be from B implies C, and the remaining assumptions we prove C. Still seems possible, right? So we haven't given anything away. So we could apply left rule here, we could apply left rule here. Okay. Now let's say we apply the left rule here. Okay. So now from A we can prove A, so proving this is very easy. And then we add B to our context. Okay, now at this point, we can do the exact same thing again. Right? We can again apply the left rule to this. We can apply again the left rule to this. Because we never lose any assumptions, we can continue to do that indefinitely, right? At some point, we can actually decide to make progress in the proof. And let's say, now that we know A and B, we should be able to do C from this, right? Okay. But in effect, in the sequence calculus, there are infinitely many proofs of this, okay? Okay. So now we want to arrange it so there's just one single proof of this instead of infinitely many. That's a pretty big reduction in the search space, okay? All the way down to 1, okay? Okay, so how we can arrange it is essentially only one proof of this, okay? You can see that it would be a very nice reduction of the search space, right? If we were so directed that there's only one way to really prove this anymore, okay? Okay, so the idea behind the focusing part, okay, so the inversion part we already did. Behind the focusing part is that at a given point in the proof search, we can pick an assumption, okay, and we have to make the right choice, so this is non-deterministically, but we can pick an assumption and apply a sequence of the non-invertible rules to that one assumption only, okay? And don't look at anything else, okay? So the rule for that is the focusing rule. Put it here. So if we have gamma, and we're trying to prove C, then if we have a negative formula in gamma, we can make a copy of that, focus on it, and try to prove C. Okay? So we have to make a copy because we may need it again. But now the whole idea is that this thing in brackets means we're focused on that, and all our left rules have to just work on that formula. We're not allowed to look at gamma. Okay? And so this is the focus left rule. Okay, and the focus right rule, you might be able to guess. If you're trying to prove C, and C is positive, we can decide we'll focus on the right-hand side and just break down the right-hand side. Okay? Now, there's a choice involved. We have to make the right choice. But once we make the choice, we can continue to apply rules just of this one assumption. So what happens here? So in this case, let's make the choice of A implies B implies C. So let's call this thing here gamma 0, okay, because that's not going to change. So at this point, we have gamma 0. We have A implies B implies C in focus. And we're trying to prove C. Okay. All right, so now what is the left rule? Well, the left rule is just the ordinary left rule, except it's restricted to apply only to something in focus. That's the big restriction. So what does the left rule say? Well, the left rule says is that from gamma 0, we have to be able to prove A in focus. Okay? And the second part is from gamma 0, and now B implies C in focus, we have to prove C. So that's an application of the implication left rule now. Okay. Now there's a small change from the previous left rule for implication. Anybody see what that is? If you forget about the brackets, it's not quite the same as the rule we had before.
You are throwing away the focus assumption. You are throwing away the focus assumption.
Exactly. So in the previous rule, when we had the A implies B left rule, we kept a copy of it, like here in the example, right? We're very careful to keep a copy of it. Here we're throwing it away, okay? And again, the justification for being able to do that, I mean, there's a proof that this all works. But the intuitive justification is because before we focus something on the left, we copy it out of the context. So we copied it before, so now we can throw it away. We can decompose it, but we don't need to keep it. Okay, so now we should continue here, okay? So here we come to an atom So we should, at this point here, lose focus. Okay? So we from gamma 0, we have to prove A. Because let's just say that all the atoms that I want here in this setting, all the atoms are considered negative. Right? So this is a choice that I make. So at this point, when we're focused on something negative on the right, we will lose the focus. We come back to one of these sequences. Okay? Now here, we are forced to imply the implication left rule. So from gamma 0, we have to apply B in focus. And from gamma 0 together with C, prove C. And so here we lose focus. So from gamma 0, we have to prove B. And, okay. So I'll fill that now. Are we okay with what's going on so far? So let's write down the rule just to make sure. Maybe I'll write the rules down over here. Make sure we understand what they are. Yeah? Yeah.
So what justifies to lose from? To lose the focus for A?
Okay, just hang on to that question while I write the rules. Okay, we'll see it. The rule for implication looks like this. We have gamma, we have A implies B in focus, while we're trying to prove some C. And we break it down to prove A in focus, and then gamma with B in focus, we've improved C, and that's the implication left rule. Okay? So now the question is, when do we lose focus? Okay? So the idea is the following. When you focus on something on the left, it's going to be negative, and we'll continue to keep this in focus as long as it's negative. As long as the left rule is non-invertible, we're going to continue that in focus. And so that means we drop out of focus when on the left-hand side, okay, we have a formula which is positive. Okay, does that make sense? So we decompose it as long as we're still negative. Okay. When we find something positive, okay, then we go to here. And now, because it's positive on the left-hand side, an invertible rule will apply. So this could be something like or falsehood. Okay? So we'll get back to one of these sequences, and we apply now the invertible rules. Are we okay on that? On the right-hand side, the idea is if we're focused on something negative, we drop out of focus. Okay, because now, if it's negative on the right, we can apply an inversion rule, an invertible rule. There's no point, or it's actually incorrect to stay in focus, but we now apply invertible rule. Okay, so therefore, in this example, if this is a negative atom, and it's in focus on the right, then we lose focus because it's a negative formula, including a negative atom. If A was positive, then the rules of the game change. Okay, so we'll come to atoms in a second. Okay. So let's do atoms now then. Okay. So the question is, what happens when I'm focused on a negative atom? Okay. According to this rule, I'm not allowed to drop out of focus, right? Because it's not positive, it's a negative atom. And in fact, we are in the situation if we make all atoms negative, right? We have a negative atom here and we're in focus. So we can't drop out of focus because it's not positive. There's nothing invertible. So what we do here is we finish off the proof with the identity rule if this negative atom matches this one over here. Okay? So here we apply the identity for negative atoms. Okay? So we have a new rule. If we have gamma and we have a negative atom in focus while we're trying to prove P, then we use the negative identity rule. So the interesting counterpart to that is actually the following, which is much more important in some sense. If you have P minus, on the right-hand side you have Q, okay, or actually any formula that's not, any formula on the right-hand side that's not equal to P, let me just write it for Q, where P is different from Q, then you fail. So I shouldn't write a line here because it's not actually a proof. Okay. So So you cannot focus. The focusing fails if you try to focus on something that's different from the conclusion you're trying to prove. Okay. Now, conversely, if we're focused on a positive atom on the right, okay, then we can't drop out of focus because we're only allowed to drop out of focus when we hit something negative, right? And this is not something negative. It's a positive atom. We can't break it down any further because we're at a positive atom. So we succeed if P is already in gamma. So if we already have that assumption exactly matching what we're trying to prove. And the important part of that is if you have gamma and you're focused on P plus, then you fail if P plus is not in gamma. Okay.
What is the difference about failing and not having a rule?
It's the same thing. I'm just writing it out explicitly to remind you that if no rule applies, you have to fail at that point. Okay? Because somehow the very important part about focusing is the places where you cannot continue, because we're trying to remove many different proofs. So I'm just being explicit about it. So it's the same thing as having no rule. Okay? So therefore, you fail in your proof construction attempt. Right? It's the same thing. Other questions? Okay, so let's get back to the example. Okay, so because this is a negative atom and I have it on the right-hand side, I can apply the identity rule over here. Now, how do I continue at that point? Yeah?
Adding the positivity annotations to all the atoms just repeating, or do you actually lose annotation when you have that negative identity rule?
Did I make a mistake there? Which one?
This is the same P.
Okay.
So what happens for every atom P, Q, R, and so on, you need to decide on whether it's positive or negative, and all the occurrences need to get the same annotation.
Okay.
All the occurrences are what? So you choose it when you make that choice.
You make that choice when you're given a theorem that you're supposed to prove.
Okay, so very good.
Yeah. At that point, you make the choice. All the atoms are positive. I mean, for each atom, you can separately decide whether it's positive or negative. So, for example, in this theorem, I could decide that A is positive, C is negative, and B is positive. Okay. I'm building a theorem prover, which I did with the student Sean McLaughlin, that's based on these principles. We never found really good
Deciding what should be positive and negative. Okay. So in some sense, it's an open question. For this example, I want to make everything negative. Okay, just to keep things simple. Okay. So make everything negative. Okay. What is the next thing we do in this proof of A? So remember, this is gamma 0. Okay. What can we do? Can we focus on this assumption? We cannot focus on this assumption while trying to prove A, because we decompose it just the same way, except in the end we're focused on on C, and our conclusion is A, so they don't match, right? You see that? So we cannot, to prove this, we cannot focus on this because this C here, which is a negative atom, does not match the A over here, okay? Which is a negative atom, okay? Can we focus on A implies B? No, because the B that we get into the context doesn't match the conclusion we're trying to prove, so we cannot focus on that. So the only thing we can do is focus on this, right? Okay, so we focus on A. While we try to prove A, and this is negative, so we can use a negative identity rule. How do we prove this? Can we focus on this? No, because the C doesn't match the conclusion B. Can we focus on A? No, because it doesn't match the conclusion B. So we have to focus on this, okay? And so if I expand it down here, gamma 0 proves B. If gamma 0, A implies B in focus, proves B. We break this down, gamma 0 together with B has to prove B, and here from gamma 0 we have to prove A in focus, Here we drop out of focus, and here we use the identity rule, and the two match. And now this we prove by focusing on this A again, right? Okay? Okay, so it turns out, if you go back to the very beginning when we're trying to prove C, and these are our assumptions, okay? We can focus on this because this C matches this C. We cannot focus on this because the B doesn't match a C. We cannot focus on this because the A and the C are different, okay? Yeah?
Focusing brackets, they are part of the judgment. They are not part of the formulas, I suppose.
Right.
So you can only have one formula focus at the same time.
Exactly.
Okay.
Right. So it's a very important distinction that in any sequence that you write down, there can be only one formula in focus.
So you have like three judgments, namely non-focus, one focus on the left and one focus on the right.
Okay, so depends on how you count, right? So you have a left formula, a left focus formula, and a right focus formula. There would be four.
What's the fourth?
Focus formula on the right. Because of the sequence calculus, we distinguish between an assumption on the left as a judgment and the thing we're trying to prove on the right. So left and right prove are two different judgments.
Oh, so you may have a formula focused on both the left and right hand side.
Not at the same time, but in our universe of possible judgments, we have to have those four different ones.
Okay.
Can you say the other two again?
Okay. It's a hypothesis on the left, it's a conclusion on the right for the first two. It's a focus on the left, and it's a focus on the right of the next two. So that's why we do four.
Is the distinction here between active and focused, where the judgment always has an active formula on the left or the right?
I think there's confusion about the word judgment.
Okay.
When you say judgment in the present context, are you talking about the whole phrase gamma arrow C, or are you talking about the individual elements of gamma?
No. I'm talking about the judgments that are ascribed to the propositions in the sequence.
So what's your word for the whole statement?
The whole statement is a hypothetical judgment.
Okay. So I think the original question was there are three forms of hypothetical judgment. One with no focus, one with focus on the left, and one with focus on the right.
That's correct. Yeah. So if you count that way, then that's correct.
So in your lecture notes, you use the words left and right for
Yeah.
those two judgments you're talking about?
Right. Yeah. And so now there's two new versions of that, focus on the left, focus on the right. But I can also count this other way, so that's also valid. Yeah.
So you said that we cannot focus on A or B at the beginning of the book.
Yeah.
But is that because so the conclusion of A or B is different from the right side of the judgment?
Right.
Whereas if we had A or B or I don't know B and C, then the conclusion of A or B and or B and C won't be C. And focusing on A or B with B and C would be a resolution. So
Well, you have to focus on the right thing. We're ruling out proofs radically. There's perfectly valid proofs that break down this implication first, but we're not allowing that. Okay. So in your example, you would have to focus on the right first. We're not allowing any other proofs. So we're very radical. Yeah. Right. 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 So it's very, very important, of course. The theorem, which I haven't stated yet, is that if a sequence has a proof, it has a proof with these restricted rules that are on the board. Right. And of course, not all the proofs that we had before will carry over. Only a very small subset of the proofs are now allowed. Yeah.
So the theorem you just stated is that for any assignment of positive and negative annotations to atomics,
Yeah.
And a given proof, you have a proof here, or
Yes.
given a proof, there is an assignment, of course,
No, the first thing.
Okay.
Given any assignment to the atoms, okay, if there's a proof before, in the sequence calculus, then there will be a proof in the focus.
So from practicality, the assignment, the only effect it has is efficiency.
Yeah, exactly. It organizes the search space, and the search space is very different depending on whether you make atoms positive or negative.
So this presentation is intuitionist, so there's only one conclusion.
Yeah.
So what is the benefit of having focusing on the right?
Because if you don't have focusing on the right, then you don't prevent focusing on the left. So you can be only one focus in the sequence at a time, either on the left or on the right. So if you don't have that, then you're losing that control. I should say something that what I've shown you so far is actually sometimes called weak focusing. If you want full focusing, there's an additional restriction in these two focal rules here, in this one and this one. And the restriction that is gamma and C are no longer invertible. Okay. So there's no invertible left pole for gamma, no invertible right pole for C. So that forces you to do all the inversions before you can start focusing. So it further removes non-determinism, okay, from proofs. So really there should be some additional restriction here, okay, to make sure that you can only focus on something once you've broken down the other formulas entirely. Yeah?
So I just want to make sure I understand. So atoms can have any assignment of positive and negative.
Right.
But it has to be fixed from the start, right?
Right.
So in particular, I can't decide along the way that an atom that has been positive. So
Well, okay. So you could leave it neutral at some point. It seems convenient to make it positive, but then you need to go for whole proof and make it positive everywhere.
okay.
Yeah. That's correct. The problem is if in the same subgroup the same atom is positive or negative, then you won't be able to apply the identity rule. Because the identity rule, the two identity rules, okay, require something in focus and something on the other side. And if this is positive, it's not going to work out.
In that case, the transponder can use the rule of law. So you have a gamma plus, then
That's correct. If P is positive, then you drop out of focus.
I mean, then when C is equal to A plus, then it somewhat looks like the identity rule for positive.
Then you have to focus on the right if both of them are positive, yes. But you cannot have one positive matching up with one negative. So you have to decide. The same atom has to always take the same polarity. Okay? Other questions on this? Yeah.
If you can pick an arbitrary assignment, why have positive and negative at all? I have to say, we're only going to do positive.
Okay. So sometimes you make everything negative, you get very short proofs. You make everything positive, you get very, very long proofs, and vice versa. Okay.
So like, you want to remove non-determinism here, maybe at the expense of having inefficient proofs. So why not just remove that level of non-determinism as well?
Well, if you want to build a theorem prover, right, you kind of have to decide, you want to be able to guide you want to define your search space in such a way that you can find the best proofs, that you can prove the most theorems. If I tell you ahead of time, make everything positive, make everything negative, okay, then you're actually going to have a worse theorem prover than I have. So, but it's an interesting observation that there's this freedom of choice here. And there's also a connection to logic programming. Those of you who know about logic programming, who knows here something about knows from logic programming? Okay. So here's the connection. If you think about this as a program, this is just propositional. Right? This says in Prolog you write C if A comma B, and you write this B in A. You write this as A, and you'd write the C as a goal C. Right? So in our logic programming, we're used to the idea that if you're trying to prove this goal C, you only use the rules that have C as a head, and you reduce it to the sub-goals A and B. And then when you try to prove A, you only use the rules that have A in the head, which is this one here. And then you prove B doing this. Okay? You see that the strategy make all the atoms negative, and you search in a bottom-up way, you get prologue. Okay. So that's another observation. Except that it's a generalization of prologue, because prologue doesn't have disjunction and certain forms of implication and so on. Now, if you make everything positive, okay, just to give you an idea of how it's there, if you get everything positive, make everything positive, you get something called data log, okay, where you work in the opposite direction. So in data log, what you would do with this kind of a theory is you say, well, which rules can I apply in the forward direction? So you start by saying, I know A, and then you say, okay, I can apply this rule to actually also know B. And then you know, oh, now I can apply this rule here because I know A and B, and I can conclude C. And at this point, I'm done, okay? Because any rule that I can apply gives me things that I already know. So you can apply this rule again, but you get C, you already know that. You can apply this rule again, you get C, you already know that. So we have reached what we call saturation. Now, if you want to know if C is true, you just look it up. Okay, and you say, okay, it's here. Okay, I'm done. Okay. So the idea is that focusing for all atoms negative is prologue. And if you have all atoms positive, then it's data log. Okay? And of course, these things are actually just fragments of what you can do in this logic. Okay, they're just small fragments. Okay. Yeah?
But I guess if you had first order connectives, then it really matters whether you will be able to find the proof or not. So if you have for all exist,
Yeah.
then depending on the choice, with one choice it may rule, and with the other it may yield a proof.
Right. So this logic is decidable, and proposition of fragments, these things are decidable. But with quantifiers, of course, things get more complicated, and you have to have still strategies. But the strategies are still much less non-deterministic than sequence calculus is. Okay. So, okay. Any more questions with this? Yeah.
The question of choosing which I can focus on a bit.
Okay. The criterion is you don't have one. Try everything. Okay. So, but actually, we really compile the clauses, but that's a separate thing, right? I mean, you try A and it'll fail because it doesn't match C, but it'll fail very quickly because you only have to do as many steps as they're connected. Okay. Then you try this, and you say, oh, okay, it fails because the B doesn't match C. But really, what we do in the prover is you compile it into these things. Yeah.
Just to clarify, for one given coefficient, we may still have several proofs, right?
Yes. In this particular case, it happens to be just one, but there's many situations where you have multiple proofs. Yeah.
Are there some formals which, like, you can't prove it if you make the atoms positive instead of negative?
No, because of that theorem that I mentioned and didn't prove. Yeah. So the theorem says, no matter which polarity you assign to the atoms, if something can be proven in sequence calculus, then we can prove it with focusing. The proof of that is actually quite interesting. So the proof of that essentially uses the Good Elimination argument. Okay? Not on the original sequence calculus, but on these focus sequence. Okay? But it proceeds very much the same way. Okay? Or at least that's the key step in the proof, is to eliminate. Any more questions? Yeah? In this particular case? No, in general, no.
Okay, so just finally long, but could be infinitely many.
Right. Well, every proof, in this thing, we don't have any co-inductive proposition, so every proof is finite, right? But you can still have infinitely many proofs.
What do we gain?
Okay, what you gain is, in general, the reduction of a vast search space with many choices to a much smaller search space with many fewer choices. But still, in many cases, infinitely many. Okay. So you can arrange that in the propositional case, because propositional intuition logic is decidable, that you can cut it off with a variety of methods. But of course, we're really interested in first order and type theory and so on. And then no matter what you do, it's still going to be undecidable. Right? But you still reduce drastically the choices. And I chose this example to show that you get from infinitely many different proofs with just essentially one, just to illustrate. And this happens a lot in practice. In many theories, the kind of proofs that you want to do give you vast reduction. We can actually quantify it. So in the theorem prover, we can publish numbers about how big the search space is and how long it takes to find these proofs and so on. And it is a vast reduction. Yeah?
I'm more just curious, are there different methods of focusing with different levels in which they produce a search space? Or is this kind of the single or dominant presentation of focusing?
Okay, so in the intuitionistic case, there's essentially no choice. In the linear case, there's some small sort of variation on the way that you do focusing, which is slightly different search spaces. But here, I think this is the only one. Yeah. Right. So like I said before, by the way, that actually focusing came from linear logic, right? And this is kind of retrofitted the idea onto inclusion. So I'm going to talk about that Pierre-Louis asked me to talk about, which is polarization. And then I want to move on to the validity and necessity. Okay. So I said at the beginning, actually it's still up there. Okay. That the negative formulas look like this and the positive formula look like this. Okay. Now you make the following observation. When you're in an inversion phase, you will treat all the negative formulas kind of in the same way. You stay within the phase of inversion. Okay? So let's make this distinction not a shallow distinction, but let's make it a deep distinction. Okay? So the way we're going to do this is we're going to say a negative formula A is defined as A implies with a negative B, or A and B, which are both negative, or true, or a negative atom. And a positive formula A is defined as a disjunction of two positive formulas, or falsehood, or a positive plus. Okay? So now we've ruled out a whole bunch of formulas, which is, of course, very bad. Okay, so now we have a way to say explicitly that we go from one type of formula to another. So we have two more operators here. One says up of A plus, and the other one says downshift of A minus. Okay? So, right, so what happened to the antecedent here? Let's think about this. So the property that I want to have is that as long as I stay in this line, I want to be able to continue the same phase of my proof search. So if I'm doing inversion, I want to be able to continue to do inversion until I hit a shift. The shift is my indication I have to change phases. I want to be able to here invert on the left until I hit the downshift, which is an indication that I'm shifting phases. Okay? So if I do that, what should be on the left-hand side of an implication? It needs to be positive, right? Because if I'm decomposing on the right-hand side by inversion, then I continue to be invertible on the negative formula because that's going to be on the right. But the A is going to be moved to the left, so the invertible things on the left are positive, right? So this needs to be positive. Okay. Okay, so this is a so-called polarized form. If you look at the polarized form of a proposition, you can always tell exactly how long the phase is going to be, inversion or focusing, because it's going to be until you hit an arrow. So you continue until you hit a shift. Okay. Now, when you're given a formula to begin with, there is different ways to put shifts in it to make it work out. Okay. So let's see. So for example, if I have a formula that says A and B implies C, okay? So what is this formula, positive or negative? Negative, okay. So that means C should be, if I want to put no shift in it, C should be negative. And the left-hand side should be something, negative.
The left-hand side should be something positive, right? Is A and B positive? No, it's negative, so I need to put a shift in, right? Which kind, up or down? Down of A and B. And let's say A and B are also negative, just to make it easy. So in this case, I could get by with just one shift, right, in order to polarize this formula. But I could also do this one, down, up. Oops, is it up, down? Up, down of C minus. Okay, I can also put a double shift in here, and that's another valid polarization. Okay. Could you say it again?
Many double shifts as you wish.
That's right.
Any arbitrary place.
Exactly. You can put as many double shifts in.
The reason you might ask is, why do you want double shifts? Why might you want double shifts? And so at the beginning when we built our theorem proof, we didn't have them. Okay. We just always polarized every formula in a maximal way, which means that we only put a shift where was necessary. Okay. But the problem is the following: the or left rule. Is it still up? No. Okay. So the or left rule is an invertible rule. So it's distinguished cases, right? So there's some theorems where you have 25 assumptions, each of which is a disjunction. Okay. If you're forced to invert on these, you get 2 to the 25 different branches in your proof. Okay. And it's certainly sound. It's complete. You can do it, except we'll just run into this exponential blow-up problem. So what you want to do is you want to block some of these so that you don't actually build this vast space of possible proofs. Even though it's safe, so in terms of decidability, it's not safe in terms of computation complexity. So when we actually analyze, when we look at the original theorem for this kind of exponential explosion and put in some double shifts to prevent these things from exploding. Okay. Okay, so now there are other uses of polarities that have to do with programming languages and has to do with the proof term assignment for these things, and some things are computations, are values, and so on. Yeah.
Is there a unique manually annotated with up and down arrows formula?
Yes, if you decide on the polarity of all the atoms, as soon as you decide on that, then there's a minimal one. Yeah.
And that's unique.
That's unique. Yeah.
If you add double shifts, you have search phase, right?
Yes.
So you lose some unicity for all vectors.
You what?
It's a compromise between a unicity of proofs and the determinants of your solver.
Right. Yeah. And sometimes you need to make a compromise, so you won't be able to prove it. Okay. So there's much more to say about focusing because there's a lot of connections to programming languages with the proof term assignments that I didn't talk about here. Hopefully, Peter will talk about some of them. Okay. But from the proof set point of view, from the logic point of view, is also critical. And like I said, any logic that I know admits some kind of a sequence of things.
Reduction, secant calculus, focusing. Sometimes people prefer to start with the secant calculus, which seems particularly appropriate for classical logic. Sometimes people start here, but no matter where you start, there always seems to be a focusing version of these things. And I don't know why that is, but it seems to be the case. Okay, so now let me spend the last 15 minutes that I have or so, and I'll try to talk to you about another instance of this idea that if you want to capture some kind of intuitive concept, some computational concept in a programming language, we try to isolate what's the logical essence and then derive a programming language from that. So one thing I didn't talk about earlier, one of the reasons we do that, when we do that, we kind of do a co-evolution of a logic and a programming language, but the logic is for reasoning about those programs. Okay? So the traditional idea is that first you design a programming language, right? I don't know, Pascal. Okay? And then you spend the next 30 years trying to design a logic for reasoning about programs in this language. Okay? When we use this idea of propositions as types, we actually have a logic, we develop it hopefully properly, and we obtain a programming notation and a logic for reasoning at the same time, sort of sort of as part and parcel of our development process. Now the logics in these simple types, right, when it's just implication conjunction, the logic is very, very simple. It's not very interesting. But because we built it in a logical way, the quantifiers are there. The dependent function types are there. The sigma types are there. The kind of things that Bob talked about, they're all there because we're working within a logic/type theoretical framework. So when you want to reason about computation with quota and eval, for example, or you want to reason about monads, okay, the way we talked about it before in a logical way, if you develop it this way, it comes essentially for free. It's there, okay, which is a very nice property, okay, because you don't have to go off and spend the next 20 years developing logics for that. Yeah?
Not reason about also perhaps I would expect to have some kind of neutral logic which is the same as the programming language types. I mean, like politicians usually are not so good at reasoning about themselves.
Right, so you have to actually extend the logic far enough that it has dependent types, sigma types, quality types, and so on. So you have to continue to build, but we know how to build these. We know the principles of which we construct. Okay, so let's see if we can do that. If we can capture this idea.
So okay, it's going to have to be somewhat abbreviated. So I'm going to give you a motivating example. Okay, so I want to define an exponential function where exponential exponent and base somehow is going to be base to the exponent. Okay. Of course, this is a toy example, but of course. Okay, I'm going to write two different functions. The first one does this. So exponent of 0 is lambda b 1, and exponent of n is lambda b. Actually, let's say n plus 1 here is lambda b exponent of n and b times b. Okay, are we okay with that? Does that make sense? Okay. Okay, so that's one version. Here's another version. Exponent of 0 is lambda b1, and the exponent of n plus 1 equals. Okay. So what I'm going to do is I'm going to call a function f is exponent of n, and then I'm going to use that in. Anybody can guess what I'm going to do next? F of b times b, except I need to return a function, right? Because exp takes a natural number and gives me back a function from natural numbers to natural numbers. So I need to say lambda b here, right? Okay? Now what's the difference between these two functions? Okay, well, if they're both correct, if I didn't make a mistake, they return the same answer in the end, right? But what's the difference in their behavior? Yeah?
Generally, if you have a different language, then your pattern match.
But in this case, you will force to evaluate the recursive call anyway in a second.
Okay, so in this second one here,
number n, you will actually evaluate the recursive call, get back a function, and then build up sort of a new function out of that. And here, if you give it the number 15, you actually essentially won't do nothing. You just return a function right away. Okay. So this thing actually, you give it a number, and it returns you back a program that doesn't depend on the number anymore. With this function here, it gives you back a program, but you haven't really done anything yet. And if you know function programming, you've built a closure that contains the number n, which will continue from then on. Right? So here you build a closure. Here you don't actually build a closure with n because you actually get back the function for this argument minus 1. You see that the two behave very differently. Okay? This will run down n levels of the recursion and then return to you back a function that doesn't depend on n anymore because you kind of have unfolded it n times, and this will just do one step and return to your function like this right away. Okay. So somehow the difference between these is that this builds your residual program taking the first argument into account entirely. Okay. Anything that depends on the first argument is already taken care of, and you just build a function which has the residual program. Okay. So we're trying to capture kind of the difference between the two in such a way that in a type system, the first one will not be correct and the second one will be correct if we say completely consume your first argument. Okay. Or another way to say that is that we take a natural number as an argument and return the code for a function which goes from natural numbers to natural numbers. So this one would be the first one. And we somehow want to arrange that this will be the first one, this will be the second. The second one has this property. We take a natural number and we build some residual code for a function from nat to nat. And the second one, well, we take a natural number, then another one, and we return you the answer. We want to distinguish between the two. Okay. So in order to distinguish between the two, the way we think about it is the following. The problem with this example here is that the function that we return actually depends on this argument. Okay, that we have to build a closure that contains n. If we look at this here, the function that we return, okay, doesn't mention this argument. Okay, because we already used that in our recursive call up here. Okay, so in order to capture this, the difference between the two, okay, we want a type system where we can check that we have something which is a closed expression. Okay, something that doesn't depend anymore on this argument. Okay. Now, from the logical point of view, a closed expression is a theorem that doesn't depend on any assumptions. Okay. And so, from the logical point of view, what we say is A is valid if, without any assumption, you can prove that A is true. Okay. So, from the programming point of view, what this says is that if you have a closed term of type A, okay, then we say, well, M is evidence for the valid. Okay. For A, you can also think about it as saying that A is some kind of source expression. Okay. It's a piece of source code. It's a quoted expression. Okay, that you can work with. Okay. So this is the basic idea. We're trying to capture this in the programming language setting. Okay. So now we need to go with the flow and trying to figure out what are the laws for validity, and then do a proof term assignment to figure out what the programming language is that comes out of this. Okay. So this, if we just do it this way, okay, and don't continue from there, then things are not particularly interesting, in the sense that things become only interesting once I allow assumption that something is valid, okay, in my judgments. So my judgment is not going to look like this, and I'm not going to fully justify this, but with proof terms it would be M colon A. Without proof terms it would just be A is true. And the idea is that these are the things that we assume to be true, so B true. And these are the things that we assume to be valid, so C valid. Okay? Okay, so let's just take it from there and see what kind of principles we would get. Okay? So let's see, what principles should we worry about? We should worry about how I use the hypotheses, and I should worry about the substitution principle. Okay? So what's the substitution principle? Okay, so the substitution principle would say, if I have A valid, and I have an assumption, A valid, under which I'm trying to prove C. So this is one of these things that should be definable. Then I should be able to get C. And let's just say C true here. Okay. And so now I'm just going to annotate this. Okay. And then in the conclusion, I get all the things in delta which are supposed to be valid, and I have gamma which is supposed to be true, and this is going to be true. Okay. So if I know that A is valid, I'm allowed to make the assumption that A is valid. Okay. And then by substitution, I can get a proof down here, a proof term down here, that corresponds to the proof of the result. Okay. So what this will actually correspond to is code substitution. So normally when we bind for a variable, which is if this is A true and the variable is mentioned in X, we don't really implement it by substitution. The way we really implement it is by binding. We bind the variable to the value and we continue, right? We build an environment. Here we don't actually build an environment, but we really do substitute the code that corresponds for that, which is some kind of source code, for a variable here which stands for source code in the term that is here. Okay. So we really want to do that code substitution because we actually want to generate, okay, a closed piece of code that we can then run if we want to. Okay. All right. So now it turns out to be convenient for reasons that again are a little difficult to explain in a very limited amount of time. But we don't want the judgment A valid to ever appear on the right-hand side of a judgment. Okay. So with the lax modality for monads, we have the same thing. The assumption A lax only appeared as a conclusion. It was never an assumption. And here it's going to be dual to that. A valid is going to appear as an assumption, but it's never going to appear as a conclusion. This is actually related to invertibility and focusing. In some sense, you can think of A valid as being an invertible judgment on the right. So whenever we see that, it kind of immediately decomposes to A true, with no assumption here, which is very important, right? You're not allowed to use any truth assumption to prove that in order to conclude that it's valid. Okay. And the same thing was true for lax. If you tried to write A lax on the left-hand side because it's invertible on the left, it would disappear immediately. Okay. So these derived judgments sort of spontaneously disappear on the left or on the right. So our judgment then will be this. Our substitution rule will be this. And we have a null hypothesis rule, which is like this. If we have delta and gamma, and we have one of these source expression variables of type A and delta, then we're allowed to assume that it's actually a term of type A. Okay? Okay, and now then that's all we need. And the next thing we need to do in order to actually use this in the programming language is to internalize the judgment of validity as a proposition. Okay? So we need to introduce a modal operator, which you might guess from this, okay, it's called box. Okay? And so we do it as follows. So we need to say with the introduction rule, I'm going to leave some room for the proof terms here. When is box A true? Okay. What we want to say morally is that's the case if from delta we can prove that A is valid. But this immediately decomposes into delta, no truth assumption, A is true. So strike this because you can't actually ever see it. Okay. And so then what you get is from box A true, we can get to A true, but we empty out the context. The assumptions about the truth, ordinary variables, are not allowed to occur. Okay? And that's exactly what we wanted to rule out here. This function here should not have this type because this ordinary variable n occurs underneath this expression. So this expression is not closed. This expression is closed. It only contains one of these code variables, x, f in this case. Okay. So that's the box introduction rule. And the box elimination rule is a little bit tricky. And again, if I had more time, I would give you more of alternatives. But it has to look like this. Okay. So if in delta and gamma you can prove that box A is true, then you're allowed to assume that A is valid while you prove C is true. And then you conclude in delta and gamma C is true. Okay. So that's our elimination rule. There are other things which might you might think of that are either unsound or are not complete. Okay, there's different ways to critique these. Okay, so basically, it's sort of like the the disjunction rule, right? We have a proof of that. We're allowed to make an assumption. Whatever conclusion we get, we're allowed to repeat down here. It's also somewhat sort of related to the elimination rule in Lax logic, except this here is C true, so we don't have a restriction here the way we had there. Okay, so now let's do proof terms. Okay, so if we have a proof M of type A, then this would be box of M. Okay, so what box of M tells you, no ordinary variable occurs in this term. It's closed, containing only variables that will be bound to code and no other variables. Okay, so you can also call this quote if you want. We're quoting an expression. Okay, and here, okay, if you have a term M of type box A true, we have a term of N as C true, then we get some kind of elimination form like this. Let box U equals M in N. Okay? And then you can verify the local reduction. And the local reduction is going to be, if we do have a let box U equals box M in N, then it locally reduces to M substituted as a piece of code for U in N. Okay. So in the actual implementation, this will not be some binding, but you will actually really carry out the substitution. Okay. And there's a local expansion too, which I'll omit now. Okay. So now we can actually write just one or two programs just to see how to work with this thing. Okay, so the first program I want to write is eval. What would be the type of eval? Yeah. Box of A implies A, right? As a function, it takes some computation that will return a source expression and actually evaluates it. Okay. So how do we write this function? Well, it's going to be lambda x, where x is type box A. How do we get something of type A? Yeah, has to be a let because we have to eliminate it, right? Let box of U equals x in U. And that's okay because we have a variable rule somewhere here that we can use these. Okay. So that's evaluation. Okay. So we can evaluate a quoted expression. Now, the interesting part, and this would be your homework. Well, maybe that's too hard. Okay. But we cannot, so we can give a closed term of this type. The big point is that we cannot prove that. Right? So it's not possible to prove this in general. We cannot prove A implies box A. If we did that, then box A and A would be equivalent. Our whole program would collapse, right? But the point of this would be a function that takes a value of type A and gives you a source expression of type A. And you can't do that. You cannot take any arbitrary runtime value, which might be some kind of piece of binary code, and try to reify it into a source expression. So that's not possible. Yeah? Well, see, in order to show that you can prove that, what you have to do is you have to develop a sequence calculus, and then you have to prove cut elimination, and then you have to show that there is no proof of this, okay? Along the lines of the other assignment to show that things cannot be proven. Okay. The other thing that's interesting, you can write a composition function, which is this one, and I'll leave this as an exercise. Okay, so it says if you have a code for a function and a code for its argument, you can get the code for the result. Okay, so if you have two pieces of code, you can actually plug them together. That make sense? Okay. And you can also have a function, let me call this quote, which is this. If you have a box A, you can get a box A. So if you're given a source expression, you can then quote it again. That's okay. You can keep quoting it as often as you want, even though you cannot obviously do this, right? The whole point, like I said before, there's no function that you can write which will go from here to here. But you can put on the box if what's given to you is already in source form. Okay, then you can quote it again. Okay. Okay, and now we can change this program up here. Last thing that I'll do. I'm sorry to get so far over time, but so in order to give this type, what we do is we take the same function here, but we write let box of f equals expression of n in box of this. And this thing will have to be box of this. Let's verify our conditions. This thing underneath the box is closed, so this box is okay. When we come to this box here, well, this elimination rule works because it has this type, so we get a function f. Underneath this box, the only thing that we use is one of these code variables, and so that's okay to use this f here. No other variables used, so this use of box is okay. So in fact, this function will have that type. If I try to change this function to use that, okay, it won't work because there will be a type error right here because you're using the ordinary variable n, which is of type natural number, okay, inside here, and you're not allowed to do that. Yeah?
Other than that, we still have to unwrap the result of the
Right. You'd also have to do that. Yeah. But it wouldn't help if you try to unwrap it in here. Yeah. Okay. Okay, any questions? Yeah? Yes.
So I should have mentioned this yesterday. The version of circle that we developed, the lapse logic circle, is actually what's called a strong monad, not quite a monad. It has some additional properties. This is a co-monad. If you want a monad, then you need diamond, which is similar to what we have. Similar to circle, but not quite. And the paper which I sent around an email about, in which I discussed these things, the diamond is also discussed. Okay. So box is a co-monad.
Is a quasi-quote form admissible in this logic?
Okay, so you can give a different system of natural reduction that has a quasi-quote format, and in this system you would say backquote box of lambda b f not f comma of expression of n applied to b times b. So that would be the syntax in that language. To do that, you need to give a different form of natural reduction.
So we'll have to come up with new notions of types.
No notion of types, no notion of logic, just a different system of natural reduction. So the basic idea of validity and necessity and so on does not actually completely force the system of natural reduction that you use. It's in the paper, actually. And we proved that the two are the same from the point of view of provability. Okay, other questions? All right, sorry for going so long.
Right, Benjamin?
Yes.
Okay.